I'm the director here, and I'm thrilled that you're all here tonight. I'm very excited for this. This is one of these special events that we do on occasion, and we've got I'm going to say, if there's a superstar in the climate world, we have one of them here in San Diego, and Dr. Somerville is with us tonight. So I'm thrilled that you're able to join us. Just a couple of little housekeepings. Again, I want to remind you, if you do need to use the restroom, jump anytime, and they're up the stairs all the way to the end. Feel free anytime to go grab a glass of wine or a coffee. This is your living room as well. You're not stuck to the chair. Those of you that are at the laptops, you will help us tonight, and I'll walk you through any challenges that you might have, because you actually run the presentation tonight. For those of you that haven't been here tonight, and I saw a few people that are brand new. Who's brand new tonight? I know Delvin, you haven't been here. Oh, yes. A few people over here. Manish. Okay, great. Well, thank you for being here. You're at a place called the Sim Center. World Resource Simulation Center is the full name of this place. It is a venue that was originally designed by a man named Buckminster Fuller, most well known for geodesic domes. And he said we needed a place to get together to really grapple with the hard issues of our day. You know, where do we go? Where do we go to really engage in the tough stuff? And that's what we try to work on here, so that our mission is to visualize sustainable solutions to global and local problems, so we make more informed choices quicker. So that's the whole reason for being, so you can better understand the history of an issue. Where have we been? How did we get to where we are today? That's what we want to kind of know about the past, but aren't you really most interested in where we're headed, in the projections for the future? As a business person, as a policymaker, what are the choices and options for the future? So that's the goal, is to actually visualize those, see them more clearly, analyze costs and consequences, so again, that we make more informed choices quicker. So that's our reason for being here. Our website is up there on number 12. We do lots of events. Most of you have been to several of them over the time, and if you are a member, thank you. I would love to have you all join. If you're a member, you get to come for free. You all know that. If you're not a member, we do actually have you to at least a suggested donation at their door or online. We would love for you all to join. Every nonprofit needs income, and that's one of the ways we do it. So thank you for the members for being here. If you'd like to use this place, some of you have actually rented this place for either a business reception or a tech training or a strategic planning. That's really our wheelhouse. We do that so well. Thanasi over there in the corner, he does our marketing, and if you want to talk about using this space, talk to Thanasi right over there. And if you want to figure out the tech, where's Paul Michael? Paul Michael makes this whole system work and function. There's so many wires and computers in here, it scares me sometimes, but it does run because of Paul Michael. Thank you to those guys, and to our new staff here, Katie. Katie is helping us raise money, so if you're looking at making a contribution at scale, at a big scale, you know, that $5,000, $10,000, $25,000 gift, we need it, we would love it. Please talk to Katie about that. So thank you for being here. And where's our volunteers tonight? Pagan? Raise your hand, Pagan, and Michael, they're on the AV, so thank you. That's we do actually stream this. Now, we're not streaming it tonight, but we do tape it, and it goes immediately up on our website. So you will be able to share this with colleagues who weren't here. It goes immediately there, and Dr. Somerville will walk out with a thumb drive. So we want to get this work out to the world as well. What did I forget? Had a couple of presenters who have been here before. Admiral Len Herring has presented here before. He's the director at the California Center for Sustainable Energy. Nicole Capretz, she's now running the Climate Action Campaign, and actually, I'm going to say, authored much of the Climate Action Campaign for the city of San Diego. I think, Dr. Carrie Lowe. I called you a doctor. Attorney Carrie Lowe has been the head of the Water Implementation Task Force for the city of San Diego, and is that not an important issue right now? My gosh. You know, somebody said if we don't get a little bit more rain, California runs out of water in a year. We're going to be talking about that some more this year, so that's important too. So that's the quick background. Dr. Somerville has an incredibly long resume. And,
No.
So if you got a chance to read that, that's terrific. But I'm going to summarize it real quick. He's one of the top climate scientists on the planet. has been a part of the IPCC, the Intergovernmental Panel on Climate Change, for many, many years, which is the UN agency where the scientists got together and looked at all of those research papers and said, is this real or not? And clearly you're going to see tonight that it is. And in 2007, the IPCC and Al Gore won the Peace Prize for the work that they had done. So he was a part of that award, not him personally, but the IPCC. And a climate scientist at Scripps and UCSD, goes back to Penn State, and in a meteorological degree at, was it New York University? For a long, long time ago. It is truly an honor to have Dr. Richard Somerville here tonight. We're going to do our typical, unique way of doing a presentation. So you sitting at the PowerPoint presentations, would you go ahead and click on that PowerPoint presentation that's at the bottom of your screen? I hope I showed you all how to do it. And then most of you, if you will go to that from the current slide, we should see slides 1 through 12 come up around the room. Up in the top left-hand corner, it says from the current slide. Click on that button that says from current slide. Number 3 over there, Manesh, click up on that where it says from current slide up there. Click there. That's it. Same thing on number 2. Mimi, would you click up on there on number 2 where it says from current slide? Good, thank you. Number 4, who's on 4 over here? That's you, Jack. Click up there where it says from current slide. You have to do that here as well. Click on down to the PowerPoint, right down here. Click on that. And then I want you to click up here from current slide. We're getting it ready for you. Click OK in the middle. That'll help you. Right there. That should do it. I think. Are we good all the way around the room? I think we're good on numbers 1 through 12. Thank you very much for being here.
Great.
Yeah. Let him do his first 12 sets, first set of 12, to go through it in depth, and then we'll have a dialogue after the first 12, okay? Dr.
Right.
Somerville.
Thank you very much, Peter. Thanks to all of you for coming. I need to warn you that I have a time constraint. I hope we can finish talking about the slides. There's 42 of them in an hour and be done at 7:30, and then have a general discussion after that. But regardless of when we finish, I have to walk out that door at 8 o'clock. That's non-negotiable. So I'll just rip the microphones off and walk out the door. Don't take it personally. It's just a constraint that I can't get out of. And I'm thrilled that you're all here, and I like the idea that we have 12 slides up. You'll let me say something about all 12 of them, and then we'll have a brief talk before we put the next 12 up. I'm brand new to this, but it's very, very appealing to me. But anyway, the classroom management part is over now. Just be punctual and no long monologues, please. No hobby horses. So I call this, what does a climate scientist think we should do about climate change? And I hope that an hour from now, you will have learned some new things about climate science. And I'm here just to inform you, not to advocate anything and not to tell you what policies are best. I'm just going to do my best to provide objective scientific information. You know, the science is facts and evidence, and to decide on policies, you have to add in your priorities and your values and so on. But I think the science itself should be nonpartisan. There aren't any liberal or conservative satellites. There aren't any Republican or Democratic thermometers. And I believe that wise policy can be informed by sound science. And so if you decide at the end of the hour that the science I've talked about is informative and maybe useful, then I will have done my job. On over here, in the second slide, you can see some evidence of how old this science is. This is the equipment used by John Tyndall, who published in 1861, more than 150 years ago, his results that carbon dioxide and water vapor and several other gases that are present in the atmosphere do absorb heat energy or infrared radiation. And that was a clear empirical finding. He put the greenhouse effect on a firm observational basis. He was one of the great experimental physicists of his day. He was an Irishman who worked in London. And I've gone through his paper in detail, and he knew what he was doing. And there was another good scientist, a Swede named Svante Arrhenius, who later in the 1800s, in the 1890s actually, did the first calculations as to how much the world would warm if you added a certain amount of carbon dioxide to it. And he was no slouch either. He later won a Nobel Prize, one of the first Nobel Prizes. He was a chemist, and he knew what Tyndall had done, And he got the right answer as to how sensitive the climate is to carbon dioxide to within a factor of 2 based on our best modern estimates. So in the 1800s, we had both an experimental laboratory demonstration that carbon dioxide could warm the planet if you added it to the atmosphere, and then a calculation of by how much it would. And that, I think, set the stage for this person here, whom I'd like to talk about. He spent his whole career here in San Diego at Scripps Institution of Oceanography, where I work. And I knew him for the last 25 years of his life. Keeling gets the credit for measuring the amount of carbon dioxide in the atmosphere. He invented the instrument. He nailed the problem. He put the instrument near the top of a volcano Mauna Loa in Hawaii, knowing that that would give you a representative value for the whole world. And he measured the amount of carbon dioxide in the atmosphere starting in 1958, when in these units it was 314. And here you can see the first few years. You can see the ups and downs each year. That's because the plants in the world take in carbon dioxide and deplete it from the atmosphere in the spring when they put out leaves and photosynthesize, and when they respire in the fall, it goes back up. So Keeling made this measurement, showed that it was increasing, discovered the annual variation, showed that it was due to plants, showed that the main source of the added carbon dioxide was burning fossil fuels, coal and oil and natural gas. So he gets credit for all of that. And this graph of his results extended out till today is known as the Keeling curve. It's the most famous graph in earth science. And you can see the numbers. What was 314 in 1958 is around 400 today. And through clever scientific detective work, we know what it was in earlier times. Keeling wasn't there to measure it, but there's air trapped in bubbles in ice in Greenland and Antarctica that can be cored and dated and analyzed. So we know that in the 1800s, it was around 280 in these units. So it's gone up about 40%. And the cause of the increase is entirely human caused. Burning fossil fuels is the big part of it, but roughly 20% of the rise is due to land use changes, especially deforestation. But the rise is entirely human caused. Over here, you're looking at the global temperature record since 1880. There weren't really enough good measurements before that to make a meaningful global average. This is the global average year by year. Each bar is a year for the temperature of the atmosphere near the surface of the Earth, globally average. And here's the mean value for that time. Blue means lower than that, red means higher than that. So you can see it's been warming. You can see that all the warmest years are recent years. You can see that the warming is very irregular. There are spikes and troughs. In general, those are due to natural variations. The high bars are mostly El Nino years. The low ones are mostly La Nina years. Years with strong volcanic eruptions can also temporarily lower the temperature. But there's a rise there. And the black line here is carbon dioxide. Here's the scale for that, which is just a smoothed version of Keeling's graph. That doesn't prove causality, you know. It's correlation, but a lot of other things went up over the last 100 years too. Hemlines, for example, or the Dow Jones average, or the world's population. But we've done enough detective work now to know that this warming is overwhelmingly human caused, and I'll say a bit about that as we go along. And if you smooth this curve out by binning it by decades, you get this here. So each bar here is a decade, and you can read it here. In the first decade of the 2000s, every year was warmer than the 1990 average, which is these, and in the 1990s, every year was warmer than the 1980s average. So the warmest year on record by a tiny fraction of a degree was last year, 2014, and all of the warmest years are recent years, and the only one before 2000 is 1998, which was an El Nino year. When we say that we know the world is warming, we know a lot more than the measurement of the average atmospheric temperature near the surface of the Earth. And in fact, that's not a particularly good measurement. We are interested in it because that's where we live, in the atmosphere near the surface of the Earth. But in fact, of the heat that's been gained by the Earth system due to the extra carbon dioxide and other heat-trapping gases in the atmosphere, only 2 or 3% is in the atmosphere, and 93% or so is in the ocean. So the ocean has absorbed most of the warming, and that has profound consequences, which I'm going to come to shortly. But here are some of the indications. These are observations. white arrows are increasing trends, black arrows are decreasing trends, and all of them indicate a warming world. So as I said, the temperature of the ocean surface is going, so is the ocean heat content in the deep ocean. That's a great triumph of science, by the way. There's an array of 3,500 floats in all the oceans of the world. Much of that system was developed by Scripps. It's an international system now. These floats are pre-assigned a depth, and they float around at that depth, and from time to time they come to the surface, transmit their data to a satellite, and sink back down to their depth, measuring as they rise and fall. It's an extraordinary advance in observational technology. Because the ocean is warming, and because water is being added to the ocean from melting ice on land, sea level is rising. We'll talk more about that too. So the air is warm. There's more water vapor in the atmosphere because warm air holds more water than cold air. So the warming speeds up the whole hydrologic cycle. And in fact, the warming caused by the carbon dioxide, because it warms the atmosphere, it humidifies the atmosphere. So more water is evaporated, and that the water vapor itself is a very powerful greenhouse gas or heat trapping gas. So it adds to the warming. And on land, temperature is also going up more than in the ocean. The black arrows are things that are going down. Glaciers, ice sheets, Arctic sea ice, and snow cover. Glaciers are in retreat worldwide here. We'll talk about that as well. So people wonder if the world is really warming, and they ask, oh, this thermometer is well sighted and quality controlled and all that, as though there were some very slender thread of evidence. But in fact, there's a big, thick rope of evidence, and these are some of the strands of it. We've done a lot of diagnostic work. So when I say that the warming was caused by human influences, chiefly the addition of heat-trapping gases to the atmosphere, we've thought about all the other possibilities. The world does have climate change because of natural possibilities. So, for example, ice ages come and go. But we know why they come and go. And they come and go because the Earth's orbit makes changes over long periods of time, thousands, tens of thousands, hundreds of thousands of years. And that doesn't change much the total amount of energy we get from the sun, but it changes the way that sunlight is distributed over the surface of the Earth by latitude and by season. And we can hindcast that. It's perfectly predictable and hindcastable as well as forecastable. And the timing of it coincides with the geological evidence for when ice ages started and when we came out of ice ages. So that's what causes ice ages. It's a mechanism that's now understood and tested and is solid science. But it's too weak and too slow to be responsible for this big warming that we've seen in the last 5 decades or so. Similarly, we measure the output of the sun, and here it is. It has, you can see the 11-year cycle. It rises and falls, but the sun is the red line down here. The temperature, this graph over here is now reduced to a line. The temperature has been rising, but the solar output has not been rising. In fact, the sun is slightly cooling. It's in that phase of the solar cycle right now. So we know, and it's furthermore, if you translate the effect of these little fluctuations to the effect on temperature of the Earth's atmosphere, it's 10 times too small to be responsible. So it just fails quantitatively. So it's due to this. It's due mainly to coal and oil and natural gas. You can see the explosive growth in the use of these emissions. Cement manufacture contributes a little, and there's another 20% not shown here that's contributed from land use changes like deforestation. But it's mainly this, the fact that in recent years especially, the use of coal and oil and natural gas, which became discernible shortly after the Industrial Revolution, has really grown. I want to say a little bit about a piece of research here. This was a paper published in 2007, the year that the 4th IPCC, Intergovernmental Panel on Climate Change Assessment, came out. I'm a co-author of that assessment, and I'm a co-author of this paper. And what we did was we looked at what things had happened, and what's shown here is carbon dioxide at the top, temperature at the bottom, and sea level, temperature in the middle, sea level at the bottom. And what you see here, it's not good graphs, I apologize for that. But what you see here are both measurements of what actually happened. You can see the ups and downs of temperatures and the smooth value here, and the range that the IPCC in its previous reports had predicted would happen. And what we concluded was carbon dioxide had grown pretty much as had been foreseen. Temperature was, that's this red line here, had risen near the top of the IPCC range. And sea level was at the very top of the IPCC range. And we concluded in this paper what you see here, that previous projections have not exaggerated, but may in some respects even have underestimated the change. There have been a number of surprises. And that's one of them, where the predictions of the IPCC, which are apolitical, but which are intellectually conservative, scientists don't like to go beyond the data, they're not publishing hunches and speculations, where it turned out that the world's climate had changed at the high end of the rate at which the science had thought it would change. And here's a special example of that. Every year in the Arctic, the sea ice reaches a seasonal minimum in September. It's the end of the melting season, just before the beginning of the ice forming season. And if you look at that, you see that a typical year before 2000, this is 1984, has about twice as much sea ice extent as a typical year after 2000. This is 2012, for example. So this is half of that. And it's thinning too. So the volume, which is the product of this areal extent and the thickness, is decreasing by even more than 50%. So that's worrisome. And it's an example, and I'm about to show you another one, of something that changed even faster than we thought. Now, Peter is going to run you through the trick here, but we'll pause for brief discussion, quick comments or questions before we go on to the next 12 slides.
Questions about these first 12?
Yeah.
Yes, David in the back. Come on, come up. You got to speak into the microphone.
Brief questions, and I'll try to give brief answers, please.
Okay. First, quick question is on the Keeling curve.
Yep.
For parts per million. Is that molecules?
Yes.
Per million? It is.
This is parts per million by volume, which you chemists will know is equivalent to molecules per million molecules. So this is out of million molecules of air, 314 then, 400 now would be CO2.
Okay, fair enough. Second part was in terms like Kirk Smith. I don't know if you know him from UC Berkeley. He says that by reducing the amount of methane, because it has a very short lifetime in the atmosphere, that we can keep from going over the climate cliff relatively quickly.
Yeah, that was, you had forewarned me, I think,
okay.
of this question would come up. I said other heat-trapping gases, and I'm not going to take the time to describe them all. But if you compare them, the CO2 has so far a radiative forcing, that is the technical term for an impact on the heating of the atmosphere and the Earth system, that's 4 times that of methane. So methane's important. But the good thing about methane is it doesn't last in the atmosphere very long. Much of it goes away in a few years. Much of CO2 lasts for thousands of years. And so you have to factor that in. The third most important man-made gas is nitrous oxide, and that CO2, that has a long lifetime, but CO2 has 10 times the effect now. So when we say CO2, we're using that as a shorthand term for a number of gases, which that's 3, and also some particles. Some small particles have the same property of adding to the heating of the atmosphere. The longer you look into the future, the more important CO2 is, because we're putting it into the atmosphere at a great rate. That's what that picture shows, that picture. And it lasts a long time.
Another question?
Doc, can you explain for the non-meteorological folks in the crowd why the increase in water vapor does not equate to an increase in precipitation on a global scale?
The question was why the increase in water vapor doesn't increase precipitation globally. It does, but only a bit. It redistributes it. And the water vapor is also a greenhouse gas. It's an important greenhouse gas, but we can't control the amount of water vapor in the atmosphere. So if you dried out the atmosphere, say, it would quickly humidify again. Or if you live in Palm Springs and you're sprinkling everybody's lawn and you're adding water vapor to the atmosphere, it doesn't stay there. It goes back down to the natural level, which depends very strongly on the temperature. But I'll say in a minute about that effect of stronger precipitation, because that's important.
How do you respond to somebody who talks about how cold the winter has been in New York and in Boston?
Well, you know, global warming doesn't end seasons, and so we still have winter. And furthermore, just as the warming is uneven in time here, it's uneven in space. So it turns out that the eastern part of the United States this past winter is one of the few parts of the world that had it colder than average. So, but it's very important if you live there, but if you're computing a global average, it's a very small fraction of the average of the world. And in fact, yeah, very tiny, or less than 1%. And so similarly, there's been a cooling over the North Atlantic. And there's very recent research that suggests this is due to a weakening of the Gulf Stream. So there, you can find places where the warming isn't as strong as others, but climate deals with averages. And so we're talking here about the average.
Creating more storms? Are we having more storms as a result?
The question of the storminess is one I just want to come to in a moment. Should we?
Another question here with Art?
Yeah, had a question about, we've reached a point in all the graphs, as I understand it, there is nothing we can do to reverse it. It's going to go on. If we stopped all fossil fuel today, it would stay at this level for 1,000 years.
There's a lot of truth to what you say. The emissions, and I'll come to that, depend on the cumulative amount of carbon dioxide you've put in the atmosphere. So, and because some of the gases, especially carbon dioxide, stay there a long time, then absent a technical breakthrough, a way to pull the CO2 out of the air on large scale, for example, then you are indeed stuck with a certain degree of climate change. What you get by reducing emissions is a reduction in the rate at which the climate change continues to get stronger. We better move on.
Okay. You'll get another chance.
Yeah,
Okay,
I
so
promise you'll get another chance.
yeah. Those of you with the laptops, count to 12. Add 12 to the number of the laptop that you're on. So if you're on number 1, you should be at screen number. There's a little number in the bottom right-hand corner. So click down. You can click the down button, or you can go back. But
Great.
adding 12 to the number that you're at on your computer. So we should see 13 here, 14. I start to see it come up. That's nice. 15 should be on number 3 over there, Monesh, right?
Great.
16, 18, 19, 20.
You guys are super.
They are. So you need to go to 21. So go ahead and click through here and get to 21. On this guy.
Okay, while the clicking is happening, I'm going to start in over on this corner here. Thank you very much. What you're looking at here are projections, in this case from computer models, but I'm showing them for a reason, of what precipitation patterns, how precipitation patterns over North America will change in the last few decades of the current century, the decades just before 2100, in 4 seasons: winter, spring, summer, fall. This teal green color is more precipitation, this brown and colors here are less precipitation. So you see, for example, more precipitation over the northeastern and north central United States in winter. You see less precipitation over the southwest in spring, for example. In general, you can see that there's sort of a northwest to southeast orientation of these lines here. But these are computer projections. But if you look here at what's happened in recent years, this is the change in percent in very heavy precipitation, downpours, deluges. You see there's been much more in the northeast and considerably more in the north central and much less here. So you see this pattern of projections for late in the century reproduced in observations in recent years. So that's, to me, very interesting and makes me think that this might not be all nonsense, because this is very complicated. The physics here is very complex. It has to do with changes in storm tracks, for example, as they move across the continent, and a lot of other things. Also from computer models, this is the kind of temperature difference you talk about. This is in Fahrenheit degrees for the global average by 2100 on 2 scenarios, 2 hypothetical futures called A2 and B1. Not sexy names, but here's A2 and here's B1. A2 is continuing business as usual. We continue to rely on fossil fuels. Population grows, economic development happens, emissions continue to increase. B1 is emissions decrease, not necessarily because of regulation or policy, but simply because we're relying more on renewables or becoming more efficient. And if you look at the implications for the United States of these 2 scenarios, here they are. Here's A2, the high emissions. Here's B1 in the last years of the current century. And you can see here that under high emissions, the US, much of the US is warming by 7 or 8 or more degrees Fahrenheit. But on the low emissions, it's warming by about half of that, to say 3 or 4 degrees in most places. So it's a big difference. So in a sense, this is the choice we face. We have our hand on the thermostat that controls this. Of course, we're talking about global emissions here. You can't change the climate over San Diego by what the good people in San Diego do, because the stuff stays in the atmosphere, the winds mix it all around. So it takes a global increase in emissions to produce that and a global decrease in emissions to produce that. So it requires international cooperation. A lot of things happen, and I want to come to them, but one of the things that happens is that many important crops have yields that decline under higher temperatures, in part, these are measurements, but in part because higher temperatures are often associated with dry conditions. Higher temperatures and drought conditions such as that in California now, are often go together. Sea level continues to rise. This is the past record from satellite altimetry, from tide gauge, that's shoreline floats, and from proxy records before the instruments. But the rate of rise is increasing, and it's projected to increase still more. And this is the range, until very recently, of what you might expect by the end of the century on global average. It depends a lot on where you are because of ocean currents, because of land rising and falling. But on global average, you can get 1 to 4 feet of sea level rise by the end of the century. Very recent work that I'm going to tell you about suggests that even 4 feet may not be the limit. It might even go up to 6 feet or more. I'm going to take time to explain a nice metaphor here. Suppose you go to the ballpark and a slugger hits a home run, and he's known to be taking performance-enhancing drugs, and the person next to you says, "Did those drugs cause that homer?" And the right answer, the best answer that I know of is, that's really not a very good question, because after all, he was a slugger when he was clean, but the drugs change the odds, and you see the effects of the drugs at the end of the season. His home run productivity has gone up, he's hitting the ball further, and so on. But he can still strike out now and then. And it's a useful metaphor because it fits well with the question you often hear, did climate change or global warming cause Katrina, or cause Hurricane Sandy, or cause this or that weather extreme? And the answer really is, there's a better way to think about that. There's a better way than to ask that question, because indeed it's impossible to attribute a particular storm or a particular weather event to climate change, but the climate has changed the environment in which all weather events take place. And so, for example, sea level is higher, and the atmosphere contains more water vapor, and that increases the odds of damage from landfalling hurricanes, because flooding from the ocean and flooding from heavy rain are the two main causes of hurricane damage. So it's a little bit like saying you can't predict how a given poker hand or a given spin of the roulette wheel will turn out. But the statistics are very good, and it's what keeps casinos in business. And similarly, you can't predict when a given person will die, but the mortality statistics for large populations work fine. That's why life insurance companies can do business. So in climate, we're dealing with statistics. And with ball players on steroids, we're dealing on statistics. And climate is the statistics of weather, including extremes. And that's why we say that CO2 is the steroids of the climate system. I've summarized the last IPCC report, which is several thousand pages long for you, on only one slide, and here it is. It is warming. We've already talked about that. We are the cause of it. It hasn't stopped. I'll come to that right now, but everybody has an unpleasant relative. I call him Uncle Pete. Even though all you people think correctly, Uncle Pete comes to Thanksgiving and spoils the dinner for everybody by announcing what he's just heard on the interview, on the internet or in the blogosphere, and or on certain TV stations. And he says there hasn't been any global warming for the last 15 years. It isn't true. The heat is mainly in the sea. I said 90+%. Sea level is going up. Ice on land is shrinking. The evil twin of global warming is that the ocean's becoming more acidic. It's dilute carbonic acid, and as we add CO2, it dissolves in the sea and becomes less dilute. That has profound possible consequences for marine life. I've told you it's gone up 40% since the 1800s. It hasn't been this high in at least 800,000 years. And as I mentioned in answer to the previous question, it's the cumulative emissions that set the amount of warming, and it's by reducing emissions we can limit it. And as the questioner pointed out, the climate change we get will last a long time. Now I want to tell you about some very recent research. This is a prediction made in 1978 by a distinguished glaciologist named Mercer. He said that he is the kind of guy who walked around Antarctica and understood glaciers. He said, if we keep consuming fossil fuels, the CO2 amount in the atmosphere will double in about 50 years. And that might produce a rapid deglaciation of West Antarctica, leading to 5 meter. He was writing for scientists, so think 15 feet. Meter's about a yard. Rise in sea level. And something happened in 2014. Glaciologists who were looking at the Amundsen Sea, that's this sector of West Antarctica, this little dot over here, noticed that these glaciers here were accelerating. And they were they were accelerating very rapidly, as glaciers go. You know, glaciers have ice that flows toward the sea. And the leader of this group announced in a press conference accompanying his paper that enough observations exist now to conclude the retreat of ice in this part of West Antarctica is now unstoppable. You can't stop it. It started a process that will continue by itself. With major consequences, you're going to get 1 meter of sea level rise and probably trigger the rest of the West Antarctic ice sheet, which comes with a sea level rise of between 3 and 5 meters, say 4 on average. So this 4 plus this 1 is the 5 meters that had been predicted in 1978. And this is his paper, was published in the peer review literature, observing these things. And a modeling paper came out at the same time saying that his results are consistent with computer models of how ice sheets behave. And when we flip to the next 12 slides, not yet, but when we do, I want to show you what happened in West Antarctica to make this event happen. It's a very serious event, and so far as I know, this is a result that's accepted by the expert community. It's not going to collapse tomorrow morning. It may take a couple of centuries. But if Rignot and his colleagues are correct, it can't be stopped at this point. So one of the tipping points that we talk about, where you sort of push and push and push, and then the straw breaks the camel's back, and you've triggered something that moves under its own power. Yeah. Questions, comments on these 12?
So the timeline on this is...
One sec.
Manish here, and we'll get to you.
You can't talk without a mic.
I would like to take your attention to the rise in sea levels.
Yes.
And the 1 meter prediction that has been made worldwide. I was reading the IPCC report, and it says that if there is a 1 meter rise in the sea levels, it probably means that 15 million people in Bangladesh and 17 million in Vietnam will be displaced.
Yes.
So is there some kind of serious thought being given by climate scientists and others on how to handle these displaced climate refugees? Because in the longer term, this could eventually turn out to be a national security issue as well.
I know that very serious thought is being given to this by many sectors of society, including the US military, which regards climate change as a threat multiplier. And there's a lot of literature from the defense world on that. It can destabilize failing states, create environmental refugees, as you just mentioned, and cause many other problems. So the answer is certainly yes. But I don't think that until recently we saw a plausible prediction that this much sea level rise could occur this quickly. This is something new, and it's new science. So I present it to you as all new science is. These people aren't immortals. They could have made a mistake, but so far I don't see it.
John, right here.
What's your best guess as to when this 3 to 5 meter rise would take place?
They don't know. It's one of the things that because they don't know, they won't speculate, but it's likely to be centuries. So it could be 2 centuries, it could be a little longer, okay? But it's not going to happen tomorrow afternoon.
Over here we have Dan behind you.
What's the anticipated impact on Florida?
Oh, I think this redraws the map of the world, and places like much of Florida are not that far above sea level now, so they disappear. And we think about the Netherlands, we think about Venice and many other places.
Well, Florida has a policy not to mention climate change in any of their official publications.
I promise to keep this on science and not on politicians, but I'm aware of that aspect of Florida politics.
Robert over there.
Yeah, hi. You've discussed that there's an ever-increasing amount of water vapor that's accumulating in the atmosphere.
Yeah.
You've discussed that in certain parts of the U.S., the temperature is ever rising, which is also becoming drier areas.
Mm-hmm.
You've mentioned that in areas that are ordinarily dry could experience humid periods, but then would resort back to their original dry temperatures. In the areas that are increasing in water vapor, is the water vapor going to concentrate in those areas? Will it eventually reach a saturation point? At that saturation point, will it be nonstop rain on an ongoing basis? And will that rain contain CO2 and other contaminants? It'll just continually rain back down into those areas.
Well, the last part, it doesn't save you from the CO2. CO2 doesn't wash out of the atmosphere, so to speak. And, you know, it's a very rare gas. 0.04% is 400 parts per million. But, so you don't remove it by rain. But you can indeed increase the amount of rainfall. But the amount of water vapor in the atmosphere doesn't increase without limit because the amount the air can hold is very strongly temperature dependent. And natural processes like condensation and precipitation keep it below 100% relative humidity, so you don't see that.
Dr. Somerville, what is the effect of melting ice in Greenland, or will we get to that?
Greenland is equally threatening, and I'm not going to talk about it tonight, but we know now through satellite measurements and from observations on the surface of Greenland that both ice sheets on Greenland and Antarctica are losing mass. For a long time we didn't know that. And there's a lot of very clever scientific work that goes on here, and I wish I had time to go into it. But we can now measure the mass loss on Greenland by satellites that measure the gravity anomaly, because as the mass is lost, Greenland's gravitational pull changes. And actually a pair of satellites called GRACE moves in tandem, and the distance between one satellite and the other changes as one satellite and then the other goes over a high gravity part of the Earth, and that can be converted to a gravity anomaly. So Greenland is losing mass, and much of the surface of Greenland is melting. I'm anxious to show you the very next slide of the next set.
One more here with Deputy Bell.
One more.
Yes. Thus far in the 21st century, I believe the amount of sea level rise has been a bit over what was predicted, and the rise in temperature has been slightly underneath. And of course, the predictions for the future tend to vary with the passage of time.
Right.
I believe that if you get to the year 2100, the number 3 is important, because if you only have, say, a rise in sea level of 3 feet and a rise in temperature of 3 feet, we might be able to adapt to that fairly well. The more you get over 3, the harder things are, and if you go much over 3 in temperature, civilization starts to get cooked.
I agree with you, although I'm not allowed to use terms like civilization get cooked. But
James Lovelow agrees with me.
Yes. Okay, can we go on to the next set of slides now?
Sure. Yes, so now you have to add 12 again. So if you're at a laptop, add 24 to your number. So if you're at number 1, David, you should be at slide number 25, right? So we'll have 25 here.
Good.
And then all the way around is 25 to 36. Now, when you get to the pictures, it's going to be a little hard to actually have a number on those.
Okay, well, the second picture here is updating. I want to talk about the first one here because it's the bottom line of the story of what's happened in Antarctica. This is a cross-section of an ice sheet where it meets the sea. And let me tell you a little bit about it. This is what Mercer realized in that prediction he made in '78 and what's been observed now. The ice sheet is grounded on land, but the seaward extension of it is called an ice shelf, and it's floating. And the blue is the ocean, the brown is the land. And the place where the ice sheet is no longer grounded on land and starts to float is called the grounding line. It's this point here. So left of this, you can see the ice is resting on land, and to the right of it, you can see the ice shelf, which is floating. And very clever use of satellite data enables you to see the motion of this grounding line. And as the ice shelf more floats and more icebergs are calved off at the end, the glacier retreats and the grounding line moves to the left. And one way you can see this from satellite data is that the part of the ice that's the ice shelf that's floating moves up and down with the tides. And you can see in the satellite altimetry, this part is moving up and down because it's floating, and the part landward of the grounding line is not because it's grounded on land. So they can track the motion of the grounding line, and it's moving that way. And in this part of West Antarctica, as is shown on this picture here, the land is sloping downward as you move interior. This is towards the continental interior. So the South Pole is on your left here, if you like. And therefore, what's melting this ice and causing this to retreat is relatively warm ocean water, relatively warm, a little bit above freezing. And it follows the grounding line as it retreats to the left because the land is sloping downward that way. And these pinning points, topographic features that would help to restrict the motion of the ice, are missing there. So this is a possibility, but it's not there on these glaciers. So that you have an instability here that as the ice melts and as the grounding line retreats, warm water comes in further and further and follows it. So it's an ice shelf that's grounded on land below sea level, sometimes as much as 2,500 meters below sea level, and that is decreasing in a valley that deepens as you move landward. So this is what's happening here, and this is the instability that Mercer had foreseen and that Rignot and his colleagues are now observing. So sorry for the depth there, but I wanted to get a little bit of nerdy nits and bits in. I didn't draw this graph here, but I've named it. And what it is the rate of global emissions for the present and a future under 3 scenarios. The graph was published in 2009, right at the beginning of 2010, really. And so the message of this is that if you want to keep the global warming to less than 3.5 degrees Fahrenheit, or to have a reasonable chance of doing that, you could only put a certain amount of carbon dioxide into the atmosphere. It's the cumulative amount in the atmosphere, the cumulative emissions, if you like, that determine the warming. And that's the area under this curve. And then when the curve gets to 0 here, it means you have to stop emitting greenhouse gases, or you have no longer a reasonable chance of meeting that target. And what the message of this graph is that if you were to have emissions peak as early as 2011, which they didn't, and then they could basically glide down at a rate of only 3.5% per year. But if you waited just 4 more years until 2015, an interesting year, it would have to decrease much more rapidly, 5.5%. And if you couldn't, you, the world, couldn't have your emissions peak and then start to decline until 2020, then you've got to have them decrease at 9% per year, which economists will tell you is very unlikely to happen. For a different, higher target, then you can have more, but you still get this same kind of graph. You get a same shape, but with later times. And so what this tells you is that there's an urgency to doing this. This is not like trade tariffs or something else. If you can't get it done this decade, maybe you'll get it done next decade. This says that Mother Nature puts a time limit on how fast you have to get this done. So there's an urgency here that has to do with the physics and chemistry and biology of the climate system. And it's not an urgency that's due to ideology or politics or anything else. So you have to do this soon, and unless the world stops dithering and procrastinating, then and has very rapid, quick decreases of emissions very soon, then you're going to be stuck with a higher warming than this. This 3.6 degrees Fahrenheit or 2 degrees Celsius is the nearest thing we have to a internationally agreed upon by governments target. You know, there's not a magic number, just like there's no magic cholesterol number that, you know, below which you're guaranteed okay, above which you're guaranteed a heart attack. It's just the risk goes up as the warming goes up, as we've seen. And this is the nearest thing we have. This is a formal policy target of the European Union, and it's an aspirational goal for many other countries. I have coming up for some photographic interlude here. We're near the end. But I wanted to quote a hero of mine, Sherry Rowland, who was a hero of the ozone story in the 1980s, when it was he who, with a postdoctoral fellow, Mario Molina, now at UCSD, discovered that chlorofluorocarbons, CFCs, and similar gases were responsible for the ozone hole. And he advocated very strongly and publicly for what finally came to be, which was an international agreement forbidding their manufacture, and they're close to phased out worldwide. But one day he was asked by a reporter, what should we be doing? And here's what he said in frustration. What's the use of having a science that can make good predictions if you don't pay any attention to them, just stand around until they come true? I actually asked Rowland whether he thought this was apropos for the global warming issue, and he said certainly. I want to have this up here long enough for you to write down any of these sites. Uncle Pete, who comes to Thanksgiving with climate myths, has been refuted on a lovely website called Skeptical Science, where there's refutations of all the popular myths. You know, it's the sun, or volcanoes produce more CO2, or ice ages came and went, so this is natural, all of those things. So it's lookable, upable, it's stratified by education level, so there's simple explanations for school kids, more complicated ones for you. This is a wonderful website run by Susan Hassel, who's my partner in a large effort to make a better communication of climate science. And we teach scientists how to deal with journalists and vice versa. And there's many useful links and downloads from all of these sites here. And I immodestly recommend my own down here. Now there's a photographic interlude. And because I don't like to tell a gloom and doom story, there's 3 gloom and doom photos followed by 6 bright optimistic photos. This illustrates the point that's come up several times. This is a picture of a storm, and it could be Katrina making landfall. And it's, as I said, because there's more water vapor in the air and the sea level is higher, you increase the risk of both flooding from heavy rain and flooding from the storm surge from ocean water. You know, California is in extreme drought now, and the West is naturally arid. And furthermore, the water sources that Southern California, for example, depends on are remote water sources. The local precipitation here is a small part of the water we use. Most of the water is imported from especially the Sierra snowpack and the Colorado River. Both of those sources are shrinking. And the increased aridity has many dominoes. It'll mean higher water rates, water rationing, increased competition between urban and rural or agricultural users of water, greater wildfire danger. So there are many, many factors that flow from drought. This picture illustrates what I would call the addiction of the present world to fossil fuels. And I use that term advisedly, but the science suggests as a goal, end the addiction. It doesn't tell you which policies to do that, but it says, the science says that if you continue to use fossil fuels, absent some magical breakthrough, ability to pull large amounts of CO2 out of the atmosphere, for example, then climate change will get worse. Those are the 3 gloom and doom slides. The happy slides are that there are many things that can be done. And there's no silver bullet, but there's lots of silver buckshot. And part of it is to accelerate a transition to clean energy, especially energy from the sun, wind, and water, which is now widely available and often cost competitive. And to be encouraged, and often there's great progress being made, but not everywhere. And the question comes up, what's the best way to increase, to accelerate, to improve the transition of the world to clean energy? And there, I have a cautionary note. Everybody has their favorite policy option, but I like to remind people that most climate scientists are not policy experts. And so I'm the wrong guy to discuss the pros and cons of tax and trade versus carbon taxes, or cap and trade versus carbon taxes, for example. We live in a specialized world, and you don't ask your dentist for advice on heart surgery, and you don't ask your cardiologist for advice on a root canal, and you shouldn't ask a climate scientist for definitive, authoritative, educated guesses about this. I can tell you what I like, but I advise you to consult experts in a field. I think that climate change is a moral issue. I really think that it's imperative. It shouldn't depend on your politics, okay? That it's imperative to do more to preserve and protect this magnificent planet that we have. And it ought to be apolitical. I think also that there's an ethical issue here. It should be about how all of us want to avoid polluting and contaminating and degrading the world. And I think, moving on, there's an intergenerational issue, and it should be about how to pass on the planet undamaged and relatively intact to future generations. And to lead on to the next photo, which comes up with the next set of slides, I think there's a very strong existential issue here, that the only climate humanity has known, the one in which human civilization has developed and progress has been made, is the current climate. And that's the climate that now threatens to be replaced by something far less agreeable. So we can talk for a little bit about these slides before we move on to the final bunch.
Just 5 more slides after this, so let's have a last set of good questions. Who's?
Well, I have one about your third slide that you brought up. I know your associate, Dr. Keeling
Mm-hmm.
at Scripps. I understand his son is also investigating climate and measuring levels of oxygen as CO2 goes up. It could be that oxygen is being depleted.
Oh, I'm so glad you asked that question.
Okay, but what he said on a positive note, and that our friend in our tropical, rainforests and so are shortening their life cycle to sequester more carbon in the ground. So.
Right, that's right. It is true. It's a very interesting human interest story. Charles David Keeling's son, Ralph Keeling, is a professor at Scripps now. And one of the things he is doing is carrying on his father's measurement program of carbon dioxide. But Ralph made his initial reputation when he was still very, very young in an unbelievably clever way. When you think about it, when you form a molecule of carbon dioxide by burning fossil fuel, think of what happens when you burn gasoline in your car engine, for example. So the carbon from the gasoline mixes with the oxygen from the air in your engine and goes out the tailpipe as CO2. And it's a heat emitting reaction, and that drives the car. But therefore, as the amount of carbon goes up in the atmosphere, the amount of free oxygen is not bound up with carbon, just the plain old O2 molecule, 2 atoms of carbon, which is 20% of the atmosphere in round numbers, ought to be going down. And nobody thought you could measure the decrease in oxygen because oxygen molecule is so plentiful. So it's percentage-wise a very tiny reduction in the amount of oxygen. But Ralph Keeling figured out how to do it. So just as his father had, with incredible perseverance, learned how to measure CO2, a rare molecule, Ralph learned how to measure the decrease in oxygen, an even rarer phenomenon. So these guys, aside from working on important problems from humanity, are crackerjack chemists.
Thank you very much for a depressing conversation, but most realistic. Regrettably, I don't see civilization changing course rapidly enough. We're turning a supertanker of energy consumption. What about geoengineering? What about the science behind geoengineering?
Yeah,
or is that something you're going to cover next?
No, I'm not going to cover geoengineering. Geoengineering is the term for intentional interference with the climate system, in which you hope to counteract the inadvertent climate modification that we're doing now. We didn't plan to warm the world up. And the 2 main versions that it usually takes in discussion and research are either increasing the reflectivity of the atmosphere, painting the surface white, painting roofs white, putting reflecting particles in the air so that more sunlight is reflected away and less is therefore absorbed, or else capturing carbon and hiding it away somewhere. And my view on those is that they are very difficult and very unpredictable. And they raise all kinds of legal and ethical issues about who has the right to do it, who pays for unintended damages, who foresees the consequences. So my personal view on geoengineering is it's like taking an unlabeled pill for a disease you haven't quite diagnosed correctly, and you should do research on it. So I feel about it as I feel about nuclear war. You should do research on it, but don't try it. Just don't try it in the real world. And I very much hope that that climate change can be arrested at a level that makes geoengineering unnecessary. So for example, to put reflecting particles in the atmosphere, which is often talked about, is doable. It's expensive, but it's doable. But then you have to keep on doing it because you've basically addicted yourself to the solution. You haven't solved the whole problem. For example, if you keep emitting CO2, the ocean keeps acidifying. And you might have very unanticipated consequences. Those particles might clump in parts of the world and not in other parts of the world just because of the winds, for example. It also gets rid of blue skies, for example. So if you care about blue skies, which I do, you're going to be seeing milky white skies instead, which might be less attractive. So I think there's all kinds of downsides to geoengineering. And in fact, I think the more research is done on it, the less attractive it seems. As long as it's not well explored in terms of theories and computer simulations and small-scale experiments, people might think it's a panacea. But I very much hope that it gets more research and that we begin to explore the full realm of consequences. I'm not pessimistic. Maybe I'm not as pessimistic as you are. I showed 3 gloom and doom slides and 6 happy ones. There's the 6th one over there. And that's about my ratio. So on good days, I feel like the world could do sensible things, and sometimes it can act fast. Who would have guessed 10 years ago that the states were rushing each other to legalize gay marriage, for example? Who would have predicted that 10 years ago? And there's all kinds of examples where civilization has changed. Women have the vote. There's been a civil rights movement. South African apartheid has been abolished, and so on. We don't yet have the charismatic leaders that I see yet that are going to galvanize public opinion. But I think the political class can change their tune very quickly if the public gets exercised about this. Okay.
Hi there. You were saying about 5-meter sea level rise in about 200 years.
200 or more.
As reactionary humans and not really anticipatory humans,
Yeah.
when do you think we will see enough motivation to have political and economic will to actually react to this? Will it be in 2050? Will it be in 2025? When is the weather going to be a clear sign that this cannot be ignored anymore?
I don't know. I really don't know. I hope sooner rather than later, because we've had these predictions for a long time now. The disintegration of part of West Antarctic ice sheet was predicted 40 or 50 years ago. And so I think, sometimes I find myself wishing for a sort of mild climate catastrophe that wouldn't do too much damage but would wake people up, that was unambiguously caused. We should pass on to the last few slides, and then we can have a general discussion.
Sure, that'd be good. Why don't you go ahead and finish, and we have some check questions that are already
Great, super. So there's the last of the happy slides that I already talked about. I do think it's an issue of intergenerational equity. I've already read this list to you. There'll be a quiz later on, so you have to know these 12 firm features. And now I wanted to say a few words about the disinformation campaign, or the prevalence in our society of people who don't accept the findings of modern climate science. And I have a number of things to say about these people, but it's 7:28, so I'm not going to say them all. But I think myself that this is, as I've said, a moral and an ethical and an existential and an intergenerational issue. And I get asked, for example, what do I think about the mainstream media coverage of climate change? And my answer is it could be a lot better. So, for example, Rignot's discovery of the instability of the West Antarctic ice sheet starting got one day's play in the mainstream media when it was announced in May of 2014, and nothing since. It's still very much discussed in the scientific community. But I think there's not enough journalistic attention paid to what I think history will judge as perhaps the greatest issue of our time. And mainstream media coverage is pretty thin, and too often it's still framed as a debate between the science community like myself and people who think otherwise. And you often get invited to have an on-stage debate with some of the few credentialed climate scientists who don't accept this. There's actually outliers in all fields of science. There are retrovirus experts that don't think that HIV causes AIDS, and there are biologists that don't think that evolution by natural selection is a fundamental principle of biology, and some people don't get their kids vaccinated because they think that vaccines cause autism. And there are doctors, and there were quite a few doctors in the pay of the tobacco industry 30 years ago, saying that, well, they're not sure that cigarette smoking is linked to diseases. You can find outliers like that, but there are very few. And there's persuasive evidence that something like 97% of the climate scientists who are most actively doing research and publishing the research in peer-reviewed technical literature are persuaded of what I would call these fundamental findings of science, and who would be agreeing with what I've been saying tonight, at least when I stick to the science and don't wander off into policy speculations. And but there is an effective and well-funded disinformation campaign, and it's funded in part by fossil fuel interests, in part by their political allies. And of course, those who say that they aren't convinced of this and they don't think the science is persuasive or they think it's controversial are in fact disguising with the criticism of the science what they're really concerned about, which is the policy implications. They are afraid of and strongly opposed to the policy choices that they fear might be made were the science to be taken seriously. So they might not like government interference in free markets. They might not like taxes. They might not like American sovereignty being weakened by signing international agreements and so on. And but rather than speak frankly about their policy choices and convictions, which are all very often sincere and strongly held, they disguise their concerns by attacking the science and the scientists. So we scientists many of us begin to feel like some abortion doctors might feel. I get death threats, for example, and every time I'm prominently in the news, they spike. And there are websites from the Disinformation campaign that will print my email address, and people will send me ugly messages. So there are lots of things like that going on. There are scientists who have been muzzled by the government agencies for which they work, and it's very regrettable, I think. And I have reproduced this famous quote from Oliver Cromwell from the 17th century, that, in science we're often very sensitive to uncertainty. We don't say we're sure of something. You want positive stuff, you get it from religion with absolute certainty. But science is, we're 95% sure that all these things are true, that kind of number. But when somebody goes on TV and attacks us for being fraudulent, incompetent, hoaxes, fudging the data, and so on, or lying to keep our grants funded, they're sure of all that. They don't say they're 95% sure that I'm a hoax and a fraud. So I say to them, think it possible that you may be mistaken. Because just as people who contested the idea that HIV caused AIDS caused deaths, because AIDS patients and HIV positive patients were deterred from seeking care, there's blood on their hands. And I think history will treat the more vocal climate science deniers very, very harshly. So that's almost all I wanted to say. I thought there was one slide after this one. Okay, that's fine. We'll do without it. Then let me say that almost all the graphics that I showed in this talk are in the National Climate Assessment, which is available and downloadable online. Just search for it, and you'll find it. And they're all public domain, so the Sim Center won't get in trouble by posting them on YouTube. The photographs are all made by a wonderful photographer who's been my wife for 50 years. And I'm grateful to her. 50 years, that's tolerance with a capital T. And that is very good. And these 5 things down here, including the website I mentioned earlier that's due to my outreach colleague, communication colleague, Susan Hassel, who, by the way, was the senior science writer for this climate assessment, which is why it's so readable and so well illustrated and the graphics are so good. So I'm grateful for, scientists have to eat too and make mortgage payments, so I'm grateful to all these places here. And finally, this is what NASA calls the blue marble. And I'm sometimes asked, well, what if all this doesn't happen? What if the world can't get its act together and reduce emissions? What's plan B? And my answer is we don't have a plan B because we don't have a planet B. Thank you.
So we have some more time, and Admiral Herring is next. But I want to acknowledge, I think it's like the courage to have to tell the truth as a scientist, right? And then to have somebody attack you to the sense that to the point that they would want to give you death threats. I'm stunned by that.
No.
I want to honor your profession and your courage, and so thank you.
Well, I know we're still taping, and this will go online soon, but I'd like to say that I love the United States. It's my country, And I find it shameful that the better part of the congressional leadership, national leadership of the Republican Party, doesn't accept what we would call the fundamental findings of climate science. I really hope that turns around soon, because until it does, we're not going to get action.
So we have a few more minutes. Let's take the chance, the time that we have. Admiral Inhering.
So, Doc, as a fellow meteorologist, I appreciate and will definitely use some of your points in my next presentation. The one graph that you showed with the up arrows and down arrows is the first depiction that I've seen presented in that fashion, and most importantly, equating the up arrows to those aspects of weather which cause for the feeding and veracity of the storms that we are seeing. Can you comment on that? And then the second part, real quick, the chart that you showed with regards to the 2010, 2015, 2020.
Right.
Why did the IPCC not develop a more realistic timeline in looking at 2050? Because 2050 is way down, way too far, and the drastic measures that are required at 2050 will require virtually a shut-off.
Yes, I very much agree with you on both points. And I think the IPCC is constrained. It's constrained to present an assessment of the published peer-reviewed scientific literature. It doesn't do research. It just assesses what's out there in a way that is policy relevant without being policy prescriptive. That's their mission statement. And I think that sometimes that's interpreted very cautiously. And so the governments, the I in IPCC is intergovernmental. We work for the governments. They pay our expenses. I don't get paid for working for IPCC. The University of California, San Diego paid my salary, but they reimburse plane tickets and so on to go to meetings. And the IPCC doesn't have resources to do more. And I think, quite frankly, that clear science, clearly presented, is not something that all the governments agree would be a good idea. And so you get something that's a little bit nerdy and jargonful. I think it's hard to comprehend. I've heard that from many government sources. We're writing for the State Department, so to speak, but we're writing like the geeks we are. And the IPCC doesn't have the resources to hire science writers, graphic experts, communication specialists to write something that's more accessible, more intelligible, and, as you say, more relevant to policy. So we're hunting for a new head of IPCC. Maybe it will change.
You were bemoaning the lack of political leadership on this issue, and I think I've heard you say that in dealing with people who won't accept climate science, that one response is to say, well, if 9 out of 10 physicians were telling you that you had a severe illness, would you still worry more about the 10th one who was in doubt? And given that I don't see that argument winning over so many of the people who are in positions of power, and since you're one of the doctors, would your prescription at this point be, or at what point do you think your prescription would be, one of shifting more to an adaptation strategy and less to one of attempting to reverse the conditions?
Well, I think we can all do better at what we do. We could all work even harder, and scientists should communicate better. But I think, quite frankly, that the politicians we're concerned about will respond to the electorate eventually. Okay, the problem is there's an urgency here that doesn't bother them, that they don't buy into. I think that the adaptation issue is a serious one, and I agree with the president's science advisor, John Holdren, who's a friend of mine. He's fond of saying, we will mitigate, we will reduce climate change, and we will adapt, because some climate change is happening already and is inevitable that there'll be more, and we'll suffer. And what you get to choose is that mix. Yeah. The more you mitigate, the less you have to adapt and suffer. And I think we're already seeing examples where there's very serious adaptation and suffering going on. You don't see it yet in your tax bill. You're paying for it, but it doesn't come labeled climate damage. You know, Sandy did $70 billion worth of damage in round numbers in the Northeast mainly. And And a lot of that is self-insured, same for Katrina. But you don't pay for it as a cost of not paying attention to climate. But I think the cost will become more apparent. I think as the damage grows, and I still hope for the charismatic leader. We need our Gandhi and our Martin Luther King and our Nelson Mandela and so on. And that person who can change hearts and minds and change the world hasn't happened yet in climate.
Yes. I've spent the last over a decade in promoting electricity as a transportation fuel for plug-in electric vehicles, and I'm about to enter a new phase, and I've signed up to work with the Climate Reality Project and training with Al Gore. Where best do people that have that kind of training, where best can they put their efforts?
I think that people like that are needed in many places. Electric cars are especially good when the electricity is generated in carbon-free ways. I'm a technological optimist. I'll say that. I'm going to dodge your question, because I don't know the right answer to it's a good question. But I disagree with people who say there's so much inertia in the current system. We're locked into it. These things have long lifetimes. Because I know of many examples where systems have changed rapidly. I live in France for part of every year. A big chunk of the year is spent in France. And you learn a lot. Not to slavishly imitate, but to just see how different people do this. And France, as many people know, switched from 0 to 80% in round numbers nuclear electricity. Did it in about 30 years. Nothing to do with climate. But they showed that it was doable. And there's been rapid increase in solar usage in Germany, of all places, which has a cloudy climate. And there's been locally strong increases in wind power, for example. And so I think the fact that there's been so much progress in some countries, in some states, in some municipalities, in some industries, is encouraging. So it's one of my reasons for optimism. I'm a great fan of electric cars, and I would love to own a little tiny piece of Tesla.
To pitch our own little project, one of the things that Jeannie is doing with the San Diego Renewable Energy Society is we have a campaign right now, and Nicole Capretz's organization is a part of that, to have San Diego be a 100% renewable city. The mayor, the previous mayor, and the current mayor have signed up for that target by 2035. It's a heavy lift from where we are today, but there is action on that front right here in San Diego. So we're doing something here, and if you'd like to be involved in that, come see us. Norm.
I should say, by the way, because that comes up all the time, I am sympathetic to and in agreement with many NGOs that have climate agendas and that do various kinds of climate advocacy. I'm not a joiner because I don't want to be accused of having given up being a scientist, and I'm less objective and less believable because I belong to this or that group. So I quietly encourage them rather than march at the head of their parades. So I hope everybody understands that.
Where does reforestation fit into this picture?
Reforestation is a good thing, and reforestation helps, and reforestation helps pull carbon out of the atmosphere, convert it back to trees. There's not enough land to put forests for it to solve the whole problem. It's part of what I meant when I said there's no silver bullet, but there's silver buckshot. So it's part of the solution. And I advocate it. It also does a lot of other good. It creates habitat. It often improves the local area and so on. So I encourage it. And I like the idea, and I think I'm all for it, but it's one of the things to be done. It helps you nibble at the problem, but it doesn't wipe it away.
I had questions about the Arctic ice sheet.
A little louder, sorry.
I had question about the Arctic ice sheet. Professor David Wasdell says that the rate of change of ice area, mass, and thickness has been accelerating and moving closely towards zero. And there are many other feedback loops, like Arctic warms up 3 to 4 times more than the other areas in the world. And like the slide you showed where the warm waters are melting the ice, and as water is exposing, that's melting the ice faster. So based on all this, these scientists are telling that, and also Professor Peter Wadhams from Cambridge University, They say the Arctic sea ice will be gone in September of this year, 2015. So what have you got to do? And also the methane release from the Arctic, under the Arctic from permafrost. What do you have to do?
I can't disagree with anything you've said. The Arctic is, in some ways, the canary in the coal mine. It's the early warning place. You know, there's a powerful set of feedbacks that make the Arctic warm faster than anywhere else on Earth. And one of the big ones is that as you melt ice and snow, you reveal darker land and darker ocean under it. So instead of reflecting away so much sunlight from the bright ice and snow, you're absorbing more by the darker surface. So the Arctic is warming faster than other places. You can see permafrost in Alaska that has buildings and roads that are kind of wobbly now because the permafrost isn't permanent at all. And it causes many serious problems. My friend, retired Admiral Dave Titley says when the ice is gone, the Navy has one more ocean to patrol. And it already is, yeah. And so it makes a lot of changes. So I'm aware of the danger of release of methane and so on from clathrates and other sources in the Arctic as well. So it's very dangerous. And I think the Arctic and the Antarctic now are both showing us that polar regions can have a powerful role to play.
Yeah, it seems that the science is the science, you know, and we're going to get to that point relatively soon that, you know, the evidence is the evidence. You know, we're going to stop the fighting and the nonsense about all that. As far as the solution, though, I mean, what percentage of the solution is in the United States or North America and Western Europe? And then following up with that, you know, what's the net effect of it? What's worse, you know, climate change or India and China and Eurasia not having a middle class and all the strife that might come?
Well, I don't think that's the choice we face, quite frankly. I don't think it's a little bit like saying, do you want to eliminate malaria or are you concerned about climate? We can do both. And I think your question is to the role of the United States. The United States, in terms of emitting as a fraction of global emissions, is decreasing. And it was passed by China some time ago. And furthermore, we're becoming more efficient. You know, less CO2 release per unit of energy produced, and so on. The switch to natural gas because of fracking is part of that picture. But the United States is the only superpower, and it's very hard to. I'm doing what I said you shouldn't do, which is ask a weatherman about international politics. Okay, so you please, you know, weight this as little as you want. But my view, for what it's worth, as one citizen, is that to get international agreements, the United States has to lead. And I think a lot can be done. I go to these international conferences. There's a UN meeting every week, which is 20,000 people. They're called Conferences of the Parties, COP, C-O-P. What they're parties to is the 1990 Framework Convention on Climate Change, and which the first President Bush signed, which has as the goal to avoid a dangerous anthropogenic, that means human-caused interference with the climate system. And they haven't produced very much. And the next one their high hopes for is in Paris next December. I'll be there. But I think a bilateral agreement between the US and China has much more chance of producing something sooner. Obama and his counterparts in China have agreed that China's emissions will peak and start to decline by 2030, but they didn't say at what level they would peak. And these things don't have teeth, they're aspirational. So I'm in favor of increased pressure on governments. I tell people, ask the politician who wants your vote how that politician feels about these issues. Right now, the polls show that nobody wants to leave a damaged climate to their kids, but it's not number one in their priority list. It doesn't rank up there with economic prosperity and national security and healthcare and education. It's number 17, and so politicians can belittle the science and ignore the issue without fear of being turned out of office.
We're talking about hundreds of millions of people in the U.S. and Western Europe,
yeah.
and not talking about the billions of people
Yes.
in the rest of the world.
Yes, and I very much hope that the international agreements include, as they did, for example, in the ozone hole case, transfer of technology and money from the developed world to the developing world. It's in everybody's interest to do that. And so once again, there's much more possible than is happening. When all is said and done, much more is said than done, unfortunately.
Two final
I
quick ones.
agree
You
with-
gotta be quick, Bill, okay?
Yeah, I agree with you. It's a moral issue. And I wonder if you think maybe the charismatic leader would be the Pope.
Well, the Pope is, the good question, the Pope is widely reported to be planning to issue an encyclical on this subject in the summer of this year, and I think we all look forward to that. I think that the Dalai Lama came to UC San Diego a couple of years ago, and my colleague Ramanathan and I spent a morning with him in a public conversation. You don't have to be a Tibetan Buddhist to realize that people like the Pope and the Dalai Lama are widely revered and respected. So I think it helps very much when you have messengers of that caliber. I hope for more of them. We're getting very near the very end of the time slot.
Quick question. I'm reminded that when the Titanic hit the iceberg, the rich people made sure they were going to get the lifeboats. In fact, they locked the third-class passengers down. So with regards to environmental justice issues, how can we rephrase this so we get away from talking about electric cars for the rich and planting trees in a desert where we really don't have enough water and that's going to produce more greenhouse gas emissions? How can we reframe it so that the rich people stop saving themselves?
That's probably a good question on which to end, since you can't possibly expect me to have an answer for that. A wonderful question. Thank you all very much. Thanks.
I know there's a request to have a signature on a painting here for you.
Oh,
Would you
hi.
give him a great round of applause? That was terrific tonight.
Nice to see you too.
Beautiful photographs and.
Want to invite you back. We actually have a movie night next week.
Okay,
It's
good. What do I-
it's one that's been produced by Leonardo DiCaprio, and I forget the
Where do I
exact name.
sign?
Thanasi.
Do I
It
have
is
something
about
for
the
me to sign
solutions.
with?
It's our movie night, movies
With
that
a
make a
pen?
difference. So it'll be next Wednesday. Invite you to come back for that. Dr. Somerville, thank you again very much for having me
Thank
here.
you all
It
very
was terrific.
much. Tasha is a friend of mine, so I have to do this.
He's going to run out of